I'll just reintroduce Chris, just for those who maybe didn't hear me. Distinguished professor at Duke University, again, in computer engineering, right? Physics, and electrical engineering, just to name a few. And really the godfather and founder behind the only publicly traded, fully focused quantum computing company. And so we're here to discuss quantum computing. And I think one of the most important things as I've gone through this journey, I've had the opportunity to really participate in a lot of kind of the foundational knowledge around quantum computing. But I think you need to help demystify it and help really the group who spends a lot of time talking about bits, bytes, and other things, and compute power and capability, in your words, help the audience understand really what is quantum computing.
Okay, thank you, Kiva. It's a pleasure to be here. Thank you, Vijay, for having me, and all my friends at UCI as well. Okay, so I'll go professorial on you for a few minutes. It actually, remarkably, only takes a few minutes. The rules of quantum physics as applied to computing are actually very well defined. And actually, the rules are very simple. The problem really is that we learn, at least I learned my whole life, through the power of analogy, knowing when you throw a baseball, it's going to move a certain way and so forth. And we have, the problem with quantum physics is that there are no analogies in real life, unfortunately. But it is a theory that describes matter at the very simple levels. And the key word is isolation. When you have an isolated system, it behaves differently. You may have heard some quips, like Einstein had wonderful quotes about how quantum is so weird. So when applied to information, it's nice that quantum physics becomes, in a way, simple, because we think of the usual bits, zeros and ones, that we use to compute and store information. There's a quantum version called a quantum bit or a qubit. Now, a qubit has a 0 and 1, but it also has a superposition of 0. You can have both 0 and 1 at the same time. And they can be in arbitrary weights. It could be 50-50, 75-25, 100-0. So you're able to store, in a sense, more information in a single entity. And the good news is when you add more bits together, there's a natural Moore's law that happens. Every time you add a qubit, you've doubled the possibilities, and you can store them all. So with 2 qubits, there are 4 possibilities. There are 4 2-bit numbers. With 3 qubits, there's 8, 16, and so forth. And this is really entirely behind the power of quantum. And I'll get to the bad news in a minute, the challenges. But the numbers are truly astounding. With just 100 qubits, these could be individual atoms, just 100, a very small chunk of matter. If you have full control of 100 qubits, you can store 2 to the power 100 value states at the same time. That's more than all of the storage medium in the world right now. And it gets even better, because with just 300 of these qubits, you can store more configurations than there are atoms in the entire universe. So this, quantum computing is a very, very overhyped field for sure, but this statement is not overhyped, and that is, if we're going to compute over spaces that have more configurations than there are atoms in the universe, we have to use quantum. There's just no other way. You'd have to build a computer out of every atom in the universe, and that means there's no room for us. So,
which would be bad.
Yeah.
That's a bad outcome.
Right, that would be a bad outcome, right? The machines building, but they're not quantum machines. The good news is we can build quantum machines that have that power, that are reasonably sized. Now, the bad news, or the challenge, I should say, what makes it really hard, there are many challenges, but the problem with this superposition, for instance, if this water bottle is a bit, it's either 0 or 1, I'm telling you that if it's quantum, it can be in both places at the same time. So what does that mean? Well, we invent another rule that says that, well, that superposition only exists as long as you don't look at it. Then everything's fine. And when you do look at it, it randomly pops into one or the other outcome. So there's a conceptual leap there. It's not like a baseball, with a deterministic path. So there's a sociological edge to this field. We have to believe this theory is real, and it is. It's been tested to better accuracy than any theory in all of nature, so it's here to stay. The problem is we haven't had a use case. It was invented 100 years ago, and it describes very esoteric type physics that happens at the extreme of temperature or simplicity. But now we're going to be building computers out of this. So people have to embrace this new intuition of how information can be stored. That's a challenge. And Vijay earlier said we have what were the big words? The implementation complementarity. That struck with me because to implement quantum computers, we have to get programmers that think the quantum way, and that's a huge challenge. It's not a technology challenge, really. I'm pretty comfortable about the tech. We're building technology we'll be able to scale, but I'm more concerned about finding the application and getting it out there for people to use quantum for their problems. And machine learning and AI are probably going to be tops of that list. They're going to be the early adopters of quantum, and it's 5 years away, I think. These are going to be probably esoteric, narrow problems, but they're going to create value. And even though I'm an academic, I do understand that once you create value, that paves the way for the tech to be developed further, just like we enjoyed with silicon technology and Moore's Law.
So, Chris, the panel before us talked a lot about the value and kind of the future of the stack and the compute capability. Mm-hmm. Now, one of the key things, if you think about crypto or even just processing all of the data that everyone's processing to get to that highest level of quality that you've mentioned, that takes a lot of power. Is there an advantage over time for really quantum to help us from a sustainability perspective and a compute?
Oh, where do I start? Again, I'm not an expert. I'm not an expert on AI. My expertise is right at the very bottom. So I'm like a silicon transistor engineer in 1950, building ICs for, you know what the first application of the IC was? It was actually a hearing aid amplifier, because you could hold it in your pocket, very small, instead of a bunch of vacuum tubes. Hearing aid amplifier for the solid-state transistor, which is now underlying everything we're doing computing.
Everything that everyone has.
So I'm at the very bottom, and I'm pretty comfortable that if we build that, somebody smarter is going to come up with applications. I'm learning. I'm always a student, especially in AI and machine learning, and even biology and the structure of molecules, things like this. These are all problems that involve, to your question, that involve interesting full-stack solutions that are all in different directions. And the company that I co-founded, IonQ, we only have 300 employees. We build these machines, but we also have an applications team that works with customers from automotive to finance. We can't work with 100 different customers. We're spread too thin to do that, but we have to very carefully pick and choose what full-stack solutions we go after. And it really has to be full-stack. We have to understand the structure. We're so early in this field. We have to understand the structure of the high-level problem, and that will actually help us build the system for that particular problem. It's not like we have cache memory that we put into our phones and cameras. It's not a commodity yet. We have to build our machine, perhaps, that's optimized for a particular use case. And that's really tricky to talk about strategy. I mean, it's like we're totally blind. I mean, I can safely say in 10 years, I don't really know what the killer app for quantum is going to be. I just want to make sure that we have the hardware to make it happen.
But so you're talking fundamentally at that hardware-capable level, and we have learning models that are dedicated to specific segments. Why can't we have a computer that's purpose-built for a specific segment? That's what you're really going
exactly.
after.
It's like an ASIC in a way. That's used for very particular. It's very narrow, and it sounds like that's not a moneymaker, but I'm not worried about that now. If we find one value use case, it will be replicated in many different sectors, because the type of problem quantum computers solve, I probably gave you a hint at what they are. You can't solve problems where you have a lot of answers at the end, because remember, when you look at the answer, you only get one. Yeah. You can't get all those. We look for problems where there are lots of inputs, but they get winnowed down, or there's like a forcing function. There's one answer, like an optimization problem that might, like the traveling salesman problem is one of my favorites, because everybody knows it. What's the shortest path between, say, 500 cities on a map, visiting every city exactly once? There are so many combinations. It's like 2 to the power 500 possibilities. It's impossible for a regular computer to be able to compute over those possibilities. But there's only one answer. So these problems like this are where quantum will shine. And to get to that answer, it will be heuristic. It will be very much like what machine learning does right now. We're going to take the quantum system and kind of push it along in certain ways and have it learn the right path.
Right.
And again, I'm not an expert in there, but it's very exciting what's going on now. I am confident that we'll be able to scale our systems to be able to deal with, say, 500 cities. Our systems right now, here's tempering the hype. All quantum computer systems right now can be simulated on your laptop. So that may sound really like a downer, but we know how to scale. It's not going to be cheap, but we have recipes for doing this. And the best way to pay for that is to find a use case. So it's a little bit of a chicken and egg issue.
But you have some partners. Before we open up to questions, do you want to talk about the current partners that you have and the use cases you are exploring?
Oh, right. Yeah, I mentioned a few. We worked with Fidelity Center for Applied Technology. This is sort of the think tank behind Fidelity Finance. And they were interested in sampling from cupulas. These are multivariate. Say you have 10 stocks, and they're somewhat correlated, but they could be anti-correlated. How do you sample from that multivariate distribution given those correlations? And again, a quantum system can deal with many more correlations than you could classically. So they're interested in modeling the stock market, for instance, and that's another type of optimization problem. One of our probably best customers right now at highest level, and this means engagement with some of their engineers, is Hyundai Motors. The CEO came to visit us in Washington, D.C., and they pulled up in these black Genesis cars. I'd never had a big black. Yeah, the Genesis is the Hyundai kind of. Okay, so he gets out and he sits at the board table and he says, in 10 years we're going to have, and I thought he was going to say autonomous vehicles, right? Flying cars. So he was out there. It was very cool. They need lightweight batteries that have long charge. But they also do need the pattern recognition needed for autonomous vehicles. Right. And so these are two areas that Hyundai is very interested in. They sound totally different, but quantum computers can help solve certain vexing material problems, simulations. A lot of our high performance compute right now goes to chemistry and computing molecular structure and material structure. Getting solid state, in particular batteries of new materials, is a simulation you could do on a quantum computer. And then there's the machine learning to do generative AI for pattern recognition, classification. And it's been a wonderful collaboration with them because they have a full team. They come out to Washington, we go to Seoul, and we learn the structure of their problem. So that's been a wonderful interaction. We're also working with the US government, of course, the Air Force Research Laboratory. They want to actually fly these things on drones and have quantum networks to do communications. We didn't talk about that aspect, but one of the very well-known applications of quantum computing is breaking codes, RSA codes. This is a long way away. It's not 5 years away. It's probably something like 20 years away. But if we find that 5-year application, that 20 years is going to, I think, shrink. So
I had the pleasure of connecting with Chris Pryor, and we had a fantastic conversations. I asked a ton of different questions, some about Sesame Street. But join me in thanking Chris for his insights.